It's my pleasure to welcome you to the GMAT 41's General Physics class. The topic of this class is work, energy, and power. And so we're going to look at the concept of work, energy, as well as power. We're going to look at mathematical relationships we need in order to solve problems relating to these three quantities. First, we start with work. This is a term we use most times daily, isn't it so? When do we say that work is done? For work to be done, there must be a force, there must be a body upon which the force is acting. And of course, the force will have to move the body from one point towards another. So once a force acts on a body, causing a displacement, of course, movement from a point to another, then we say that work is done. Mathematically, work is giving us the product of force times what? Displacement. Is that okay? Sometimes you see it as force times distance. In one of our previous classes, I stated on the motion, that is actually kinematic motion, that there are certain cases that distance and displacement are similar. The first step motion, displacement and distance are equal. Is that okay? And so we can just use them interchangeably at times. But when you exhibit more than a one-step motion, of course, the concept of distance and displacement becomes very much clearer. Meanwhile, we know that displacement is a vector quantity, while distance is a scalar. So the fact that the definition mathematically of work is force times displacement, that tells us that it could be an application of something like multiplication of vectors. Of course, we encountered that under vectors, where we evaluated work as a scalar product of force and what? Displacement. In that case, the force will be given as a vector quantity, it has its component, and then the displacement also as a vector quantity, it has its component. So please take that generally, though in some cases you see distance, but in reality, this is displacement. Is that okay? Change in position. Alright, now we're going to consider work under different cases. On the board here, and in this video, we have two cases to consider. In the next video, we're going to consider further cases where we evaluate work. Now, in case one, we're looking at a case where force acts on an object, moving the object linearly in a straight path from one point to another. So we have this as the initial position and this as the final position. So we have displacement dx. Alright, this displacement is dx, change in position. Is that okay? In that case, work is equal to f dx. And of course, we know the dx there on integration is going to give us x2 minus what? x1. Because we can actually work on this and say that work is equal to f integral from x1 to x2 dx. Integral dx is going to produce x. Then you substitute the limit x2 minus x1. We arrive at this equation. So you need this equation, alright? Equation 1 for calculating work. Under a case where the force moves the object linearly from one point to another. In case 2 is a situation where the work now pulls on an object, but at an angle to the horizontal. So this is our horizontal. We know already that this force acting on this object will move this object, is that okay, from this point possibly to a given point along this line. But then the force is attached to the object in this way. You can think of a child, alright, tying a rope to, per se, whatever he or she may call a car, and then he's dragging. So the car is moving horizontally, but the force is inclined to the horizontal at an angle, alright? So the child moves this way. Under a situation like that, for the car, or the object in this case, to be moved by the child is applying the force to the rope and pulling. So work is done because displacement is covered, alright? In a situation like that, the work formula is f dx cos theta. That is the scalar definition of work. The product of the magnitude of the force, the magnitude of the displacement, then cos the angle between the two vectors. I hope I'm communicating. So along this line, distance is being covered, the force is inclined as an angle to the horizontal. Now, if we integrate this part, you know that integral dx from x1 to x2, like I explained, is going to give us, let me finally indicate that x2 minus x1. Is that okay? So, if x2 minus x1, we simply call it x. Generally, the force inclined to an angle produces a work giving us F times X cos theta. Another important formula to memorize. In the next video, we're going to consider other work terms when you're lifting an object, and of course, work done on a spring. In this video, we now want to consider other forms of work. Work in a force field and work done on an elastic material. So these two will be considered here quickly. When you're talking about work done in a force field, it's that work that is subjected to force of gravity. So we obtain it from the force of gravity. We also consider the weight of the object. Now, if you have like an object, say this marker, you can lift this object upward. The fact that you are lifting it through a vertical height, through a height, and you're applying a force, work is said to be done. Although in this case, the force comes in terms of the weight of the object. Take note also that the object can fall down freely this way, falling, being pulled down by its own weight, and it is subject to an acceleration known as what? The acceleration due to gravity. The work under such case is given simply as mgh. Is that okay? Now, you likely may have seen this formula before, the potential energy formula. Remember that work and energy are closely related terms. Without energy, you cannot do work. So this is the formula you apply when you are considering work done in a force field due to either lifting an object or the object falling down freely. Case 4 is work done in compressing or extending an elastic material. Whenever you are dealing with an elastic material, for example, a spring or a rubber, you subject your discussion there to a law known as Hooke's law, which states that provided the tolerance range of extension or the elastic limits of an elastic material is not exceeded, force is directly proportional to what? Extension of that material produced. Is that okay? So this law, we're going to use it to analyze this. Consider this diagram here. This is a spring. Now I fix the spring to this rigid wall. So this wall is fixed. Then I attach the spring to it. From this point to this point is the original length of the spring. Natural length. We refer to it as the equilibrium position. Is that okay? When the spring has not been extended, when it has not been compressed, it is at rest. That length there is called its natural length, the equilibrium position. Is that okay? Or the maximum displacement from its rest position. Sometimes you can use the term like amplitude. I don't know if you're getting me right for it. Yes, one can use that. We'll consider all of those under simple harmonic motion anyway. But let's focus on this. Now, a force is exerted on the spring and pulls the spring. You can notice that we have extension now. Are you following, right? We have extension, you can see that. So let's assume that this is the final position of the spring. Between x1 and x2, we have this extension dx. Is that okay? So with this, we can apply Hooke's law of elasticity, which tells us that force is equal to kx. K there is called the force or the stiffness constant. Is that okay? Or elastic constant. And then it's multiplied by the extension x. Okay, now if this is the first formula in this case, and we know generally that work is equal to force times displacement, we can substitute kx for this force here and you get this. Now there is a differential coefficient multiplying, which is the x. That gives us room to integrate this expression with respect to what? X. K is a constant, so you bring it out of the integral sign. You're going to have integral x dx, integrating from initial to final position of the spring. If you integrate this x, this is x raised to the power 1. So to integrate, you add 1 to the power, divide by the new power. That's going to be x raised to the power 1 plus 1, which is x raised to the power 2 divided by 2. You can say that here with the limit. So simply substitute upper limit for x. You get x2 squared minus lower limit for x. You get x1 squared. So you have x2 squared minus x1 squared. This 2 is a constant. It can come out as 1/2, 1 over 2. And then you get this formula. x2 squared minus x1 squared, if we represent it as x squared, alright, then this formula will reduce to a term like this, telling us that work done in extending or compressing an elastic material is simply equal to 1/2 the first constant times square of the extension. Alright, please take note that all the 4 cases of work analyzed so far, the force there is a constant force. It's a force that does not vary. So it's constant. The question now is, what if you are given a situation where work, all right, is obtained from a variable force? What do we do? So in the next video, we're going to consider work done under a variable, a changing force condition. Previously, we discussed cases where work is done under a certain force. The 4 previous work cases considered, we referred to such case as work done under constant force, so the force does not change. Now, what of a situation where you have a variable force, so the force is changing? All right, how can we evaluate the work done by such force? On the board here, I have this diagram. All right, I've chosen to use a 2-dimensional case problem. Take note that in general, force can be expressed in 3 dimensions as well, to where you consider the x, y, and z axis. Of course, we've encountered this under vectors and also in dynamic motion, okay? Good. So in a situation like that, we could say, like we have this diagram, this is x1, x2, y1, y2. Of course, if we are to move this object from point A to point B, remember that to locate a point in a graph, you use x and y, is that not so? So this point A has the coordinate x1, y1. Point B has the coordinate x2, y2. Now it is required to move this object from point A to B. Take note of something here, that this point A to B is not a straight line. Okay, it's a curve. It's a curve. So just imagine you have to follow a curve and then move an object with a given force to another point. But you must follow a curve. There is no straight path linking those 2 points. What work will be done under such situation? Is that okay? So that's what we're trying to evaluate here. All we need to do is to take note of the fact that the force can be expressed in 2 or 3 dimensions, okay? Our focus here, though, is going to be based on 2 dimensions. Now, the equation of the curve will be given. So you see this y is equal to f of x. Are you following? So y will be given as a function of x. So that curve will be defined by an equation. And on the basis of that, since this is the variable force, F is equal to Fxi plus Fyj. Alright, I chose to deal with 2 cases. Like I stated, generally, take note that we could have a 3-dimensional force case. So, if this is the variable force, how can we get the work? Now, quickly take your mind back to what we did when we tried to calculate work under vectors. Are you following, right? Using the component of the force and the component of the displacement. We did scalar product, dot product of the force and the displacement. And so you could have something like Fxi times Rxi. When I multiplies itself by dot product, we stated that it's going to be equal to 1. Which means that generally if you're multiplying the x component to be Fx times Rx plus Fy times Ry, where R is the displacement there, you know, plus Fz times Rz. So you see the general definition of work in such case. We are using the scalar product definition of work for analysis here. Because of course, we need to consider the displacement, and then we're going to multiply the displacement by this variable force, which already has the x, y, z axis with the unit vectors there. But when you're carrying out the multiplication, the unit vectors will all become 1 under scalar multiplication. Of course, work is a scalar quantity, we know that. Let's now go back to our 2-dimensional case. Generally, if we know that this is what the work will look like, the x is displacement in x-axis, the y is displacement in y-axis, and then the z in z-axis. Each of them multiplied by what? By fx, fy, and fz respectively. In the 2-dimensional case, this is what we are going to get. So this is the formula, look at it. Very important to memorize. This is the general form in 3 dimensions, but I've chosen to limit it to 2 cases. So all we need to do here is simple. Are you following? The equation of the force will be given to us already, where we know Fx and Fy. So if we are given a case like that, this equation of the curve will be given. All we need to do is to convert the y to what? The x. Convert what? Dy to dx. You can say that. So we'll find a way to replace this dy with dx. Once we do that, this whole expression will now be in terms of dx. Then we can integrate and obtain our result. To convert dy to dx is simple. You use the given equation y equal to f of x. Do your differentiation. Make the x subject to the formula there. Is that okay? Then solve in terms of that dx. But take note, it's true that I've stated that we convert dy into dx and solve. but one can still choose to say, no, I want to solve in terms of dy. So you will convert this dx into dy and then start what? Solving. But if we encounter a case like that in our studies, you're going to deal with converting dy to what? Dx. I usually prefer that. The next video, we're going to pick questions and solve, having analyzed all the cases of work under constant force and now under what? Variable force. On the board here, we've got this question, alright? We have to determine the work done on a lawn mower by a person who exerts a force of 75 Newton to rate at an angle of 35 degrees to the horizontal, pushing the mower 25 meters on a level ground. Have you seen a person working on a lawnmower before? Using it to clear grasses. So the person holds the lawnmower this way, you know, so you can see the force with which he's holding the lawnmower is inclined downward like this. If you trace it down to the ground, it will incline to the ground at a given angle, which the value has been given to us. So as he moves, he's pushing the lawnmower, then the lawnmower is spinning and clearing the bushes. The distance moved is 25 meters. A sketch of the diagram is really something like this. So let's say the lawnmower is here, you know. So this angle at 35 degrees. Then the force applied. The force applied, force is equal to 75 Newton. And then the distance covered, you know, when pushing this, let's say from here to this point, let's say the lawnmower was here initially, when pushing it to this point, the distance covered is 25 meters. Alright, so let's say x equal to 25 meters. So, based on this, the work we don't know. We need to recall, in a case like this, work can be evaluated using fx cos theta. Is that not so? Fx cos theta. So simply, our work is equal to 75, which is force times the distance of the displacement is 25 times cos 35. So we can evaluate this, can reach out for a calculator and see what this is going to give to us. So we have 75 times 25. We're going to multiply it by cos 35. So this is 1,535.9 work. So this is the work that is done on the lawn mower. We now have this second question on the board. It's about a boy that runs up some set of stairs. How many stairs here? 5 stairs, each of 3 meters high. The mass of the boy is 50 kilograms. We are asked to find the work done against gravity. Is that okay? So the mass of the boy is 50 kilograms. Now the boy runs up 5 stairs. What if I just decide to show the diagram of the stair, which of course is not absolutely necessary in solving for objective case of examination? You know how many? Let's say this is 1, 2, 3, 4, and 5. So these are the stairs. Okay? These are the stairs 1, 2, 3, 4, 5. Each of them is 3 meters. Each of them is 3 meters high. So if each of the stairs, the height here is equal to 3 meters. So total height will be equal to 5 times 3, which is 15 meters. So the boy actually climbed a staircase of height 15 meters. Alright, the weight of the boy, the mass of the boy rather, is 50 kg. Now we're given acceleration due to gravity to be 10 meters per square second. We have to calculate the work done against gravity. Okay? Now generally, for work done in the force field, you know, gravitational field, we need to recall that work in this case is mgh. Is that okay? And then W will now be equal to the mass of the boy is 50 multiplied by 10 acceleration due to gravity times the total height 15. So let's multiply this and see what we're going to get, alright? So that's 500 simply times 15. 500 times 15. That is 7,500 joules. You can choose to convert these to standard form, you know. There is an invisible point here because it's a whole number. So you can move the point 1, 2, 3. So it's the same as 7.5 times 10 raised to power. You move the points to the left. So the power will be plus 3. Power of 10 plus 3. So either of these could be our answer. And this is just a simple solution to this problem. Says an interesting one, right? In this video we have another question here. It's about a perfectly elastic spring which requires 0.54 joule work to stretch 6 centimeters from its equilibrium position. That's its rest position, from its natural length. Alright, what is its spring constant? B. How much work is required to stretch it an additional 6 centimeters? Let me just quickly sketch something here, alright? So if we say we fix the spring to this rigid wall, for example, now this is the natural length of the spring. Alright? Now from this rest position, let's say that from this rest position x1, is that okay? It was stretched under a force. A force pulled this and then it extended. It was stretched by this force, 6 cm. So if from here to here is the original length, then from this point to this point, can say we get our x2, which is equal to 6 centimeters. Let's take our x1 to be 0, the rest position, the equilibrium position. Is that okay? Fine. We can convert this. This is equal to 0.06 meters. Divide this 6 by 100. Remember, the work that stretched this spring from this point to this point is 0.54 joule work. Is that okay? So work that did that work, that's an extension for us, is 0.54 joules. Now the first part of the question, we have to calculate the spring constant, also known as the force constant or stiffness constant. So we're going to recall, if we want to calculate the spring constant and we know work done, already the extension is given, we have the value of x2 minus x1, you know. We recall that work done on an elastic spring is equal to 1/2 k open bracket x2 squared minus x1 squared. So we can actually substitute, this becomes 0.54 equal to 1/2 times k, we do not know, 0.06, which is the value of x2. I'm going to square it, minus x1 is 0. No need of even bothering ourselves. But let me just fix it. In case the initial position is defined, if it is given as a value which is not 0. Is that okay? You have to replace it there. We can cross multiply this term. 2 times 0.54 will give us 1.08 equal to k times 0.06 squared. Take note, in this bracket you have 0.06 squared. So the force constant will now be 1.08 over 0.06 squared. Right? Therefore, k is equal to, find out, if you divide 1.08 all over open bracket 0.06 squared, that is equal to, from here it's giving me 300. So it's going to be 300. The unit of force constant is Newton per meter. Remember, I converted to SI units. According to Hooke's law, force is equal to kx, force constant times extension. So k will be force over extension. Force is Newton, extension is in meters, SI. So you see that the unit will now be Newton per meter. We were not given the force, the value of this force here. It wasn't given to us. But you know we can calculate it, being that we know the force constant now. Can calculate it. Note, you can use F. But let me indicate it. Note, one can now use F equal to kx to obtain the force applied. Meaning that you know your x is 0.06 meters. Multiply by k, which you know 300, you get your force. Now we have to determine how much work is required to stretch this spring an additional what? 6 centimeters. This is B part of the question. So take note that initially in the first extension, alright, the work done was 0.54, which stretched the spring from its rest position, equilibrium position, to a point 6 cm. Now, if we are to still stretch this spring from here again, an additional 6 centimeters, let's say you pull it from here, move it again, that additional 6 centimeters will actually be 12 centimeters from the equilibrium position. Is that also? It's going to be 12 centimeters from the equilibrium position. Now, the work that is done to stretch it from this point to this final point of that 12 centimeters is what we are asked to find. Permit me again to redraw this diagram. We're going to have something like this. So, okay, this was the original position, which we assumed to be 0. A force pulled it, and then there was an extension. In the first case, let's say that the spring was dragged to this point. Now let's say this x2, which is the original 6 cm, converted to 0.06 meters. Again, you will now stretch it. Let this one be our F1 stretch. Is that okay? F1 stretch. In the first case. This time around, you're now stretching again. F2. So this is F2. So this is the final position. Let me take this as X3. And then we would say that X3 should be equal to an additional 6 centimeters. So from here to here is plus 6. Again, taking at this position is 6. So if you add another 6, here will be what? 12. 12 cm. That 12 cm can be converted to 0.12 meters. So that is our X3. Is that okay? We are interested in calculating the work between this point. We do not know. Does that make sense? Alright, let's go. Recall that work is equal to 1/2 times k x2 squared, right? x2 squared minus x1 squared. But in this case, due to my label, in this case, we are going to say that work is equal to 1/2 k x3 squared minus x2 squared. Is that okay? Final minus what? Initial. X3. Because of the way I labeled the position. We are interested in the work between this x2 and x3. So guys, our problem is solved. We understand the interpretation now. This is going to be work equal to 1/2 times the first constant already we got it to be 300. Alright, so note K equal to 300 Newton per meter. We obtained it in the first part. Is that okay? And once you get the first constant, the spring constant, the stiffness constant of any elastic material, remember that value is a constant, so it belongs to that material and that material, and so you can use it for different questions for that same elastic material. I'm going to multiply it by 0.12 squared minus 0.06 squared. So the work will now be equal to, this gave me 0. You made me to write this out, 300. The bracket here gave us 0.0108. Therefore, the work done in the further stretching of the spring is going to be 0.0108 times 300, then divided by 2. This gives me 1.62 joules. So this is the extra work that needs to be done to stretch the spring further from this x2 position to x3 position, an extra 6 centimeters. We have yet another question, the fourth. The question here, it reads, an object moves along a parabolic path y equal to 0.5 per meter times x squared from the origin 0, 0 to a point 2 meters, 2 meter under the action of a force F equal to 5 Newton per meter times y plus 10 Newton per meter times x j. Calculate the work done. Are you worried about this question? Please don't feel perturbed, okay? Don't be worried about it. This question is 1 + 1. When I'm done analyzing it, you will understand there is actually something we can play with. The first thing we need to understand here is that this question is work under variable force, because you can see that the force is given in dimensions, right? We have 2-dimensional case here, the I and the what? J. Is that okay? Alright, let me bring out the data given to us. That I think I can sketch this diagram for you to see clearly. Let me sketch it. So if I say that this is a parabolic path from the origin, okay, so let me say that from this origin you have 0, 0, and then let's say that the object is moved to a point here. So this is 2 meters, 2 meters. Is that okay? Under the action of a force. So there is a force that moves this. But the equation of this curve, let's write that. The equation of the curve is given as, let's see, y. Equation of the curve is given as y equal to 0.5. 0.5 times x squared. Please take note, this is the unit. Sometimes questions are presented in this way just to confuse a student. You don't need to be confused. Are you getting me right? This is unit per meter. So that per meter needs to step outside so that x squared will multiply the 0.5. So it's going to be per meter. Now we're given the force that is moving the object. Is that okay? The force moving the object this way. Now the force is given to be equal to this value here, 5yi plus 10xj. You see, I am no longer interested in this Newton per meter, they are units, okay? So let them step aside, let's see what we are doing. This is the force. Now you can see that this is a variable force. And we are asked to calculate the work done. We do not know. Work done, we don't know. So we quickly need to recall that in a case like this, work is equal to Fx times dx plus Fy times dy. That's the work formula. Having recalled this work formula, the next thing I need to do is to select the axis I want to solve with respect to. Do I want to solve with respect to x? Or do I want to solve with respect to y? You recall that in the introductory video explanation to variable force aspect of work, I stated that I prefer solving in terms of x. So we're going to convert all y to x in this formula and get our dy. That's just the thing. Alright, let's just write the work here first and see what we're going to get. It implies that work is equal to Fx. What is our Fx? That is f of x. F of x is that one that is bearing the unit vector I. Are you getting me right? Let me indicate it here. F of x is equal to 5y. And then f of y is equal to 10x. You see, under vectors, we know that the unit vector I is associated with the x-axis. And the unit vector j to what? Y-axis. Yk is to z-axis. This is a two-dimensional problem anyway. So have I and j. So all I need to do, like I was trying to explain here, is to convert all y to x and all dy to dx. Let's fix in our value and see. F of x is 5y. So I'm going to write the 5y there and then multiply by dx. 5y, then dx. I'm substituting. Fy is 10x. So it's going to be 10x multiplied by dy. So at this point, replace all y and dy using x and dx by differentiating y equal to, they gave us the equation of the curve, 0.5x squared. Is that okay? The equation of the curve gives us the value of y in terms of x, which means we no longer have problem with this y. We can replace it directly. The value is 0.5x squared. Our challenge now is this dy. So we need to go and differentiate and obtain our dy. So dy over dx. This is y, you know, y is equal to this 0.5x squared. If you differentiate this term, you're going to get 2 times 0.5, which will give us 1, then x raised to the power 2 minus 1, which is, of course, equal to x. That's the differentiation, which means that making the x subject to the formula, or making the y subject to the formula rather, because we want to get the value of dy, so we can replace it here. It will be equal to x dx. You know, you cross multiply. Is that okay? You cross multiply. So take note of this. Take note of this. And take note of this. These are the two things we are going to use in substituting. So substituting now, we're going to get our work is equal to 5. In place of y, I will fix 0.5x squared. You can say that right, in place of y. That is bearing dx there. Then plus 10x, in place of dy, I'll fix x dx. So we're going to have x dx. I think our problem is solved. What do you think? Because we've been able to reduce every term in this work to dx. So I can now simplify this term and of course integrate with respect to what? X. So this means that we're going to get w to be equal to 5 times 0.5 will give us 2.5. So this is 2.5x squared There is the x here, there is the x here, so I'll factorize the dx. 10x times x would give us 10x squared, all in bracket dx. So, all we now need to do is w equals, we can now integrate from the initial to final. See, we are solving with respect to x. So the limit you are going to pick is going to be the x coordinate in this limit here. So we are moving from this point 0 to this point 2. You know, this is x1 and this is x2. Are you following, right? So this is going to be something like x1, x2 of all these terms here, which is 2.5x squared. Of course, we can add this, you know. If you add 2.5 to 10, you're going to get 12.5x squared dx. Take note, we can add these terms because they are like terms, both bearing x squared. So, we are going to integrate this, like I stated, from 0 to 2. That's the limit. I showed it to you there. Then 12x squared dx. We have already arrived at the point where we obtain that work is equal to integral from the limit 0 to 2, 12.5 x squared dx. We obtain this. So all we need to do now is simply to integrate. Take note, the limit of integration I selected here is that of x. Take note, not that of y. The reason I selected for that of x is because I'm integrating with respect to what? X. So these are the ones I selected, 0 and 2 here. Alright? I'm emphasizing on this because suppose the limit of x and that of y are not the same here. You will now start thinking, which one do we use and why did we use that? So take note. I'm integrating with respect to x, so I am going to select the limit of x from this coordinate here, initial and final. Let us now integrate this and see what we are going to get. W is now going to be 12.5 is a constant, so it comes out of the integral sign. We have something like this. If you integrate x squared here, it's a polynomial function, so add 1 to the power, divide by the power. So this is going to give us 12.5. Open bracket, x raised to the power 3 divided by 3, then the limit 0 to what? 2. W being our work is now 12.5. The constant 3 would have to come out as a divisor. Is that okay? Denominator. Then we're going to substitute the upper limit for x and lower limit for x. Upper limit goes first, so 2 raised to the power 3 minus lower limit for x is 0 raised to the power 2. Okay, raised to the power 3. Because x is raised to the power 3 there. Now if you work on this is going to give us 12.5 divided by 3 times, the bracket here is 8, you know. 2 raised to the power 3 is 8. 0 cubed is 0, it goes off. So let us see what this gives to us. 12.5. 12.5. We're going to multiply it by 8 and then divide by 3. It's given me 33.33 joules. So this is the work done in moving this object from the origin to this point with coordinate 2, 2. So you see that the problem is a simple one, honestly. Because under vectors, we've actually seen cases where we deal with force having different dimensions. All you need to know for this question is how you got to know that this is a variable force problem. And it's simple. Force will be given as 2 or 3 dimensional problem. You can see that. Are you following? Once you're able to identify that force is a 2 or 3 dimensional problem and you are given the equation of the curve, simply use the formula W equal to f dx plus f dy, then decide the axis you want to solve, the coordinates you want to solve with respect to. I've told you I prefer solving with respect to x. Reason, in most cases the equation of the curve will be given such that y will depend on x. Y will be a function of x. So from this I can substitute for y in my equation and then I can differentiate to get dy in terms of dx, just like you saw me did while solving this problem. Once you're done with this, the rest is stories. Substitute, simplify, do your integration, and you just see your result there. In the next video, we're going to now look into the concept of energy and power.